Good evening, welcome back, or if you're new here, welcome. Tonight we're going to explore something that surrounds you, something that might be in your hand right now, glowing softly in the darkness of your room. We're going to discover how computers actually work, not in the way of a textbook or a technical manual, but slowly, calmly, moving through time like a dream. We'll begin centuries ago, with brass gears and mechanical calculators clicking in counting houses. We'll watch vacuum tubes glow orange in the 1940s, filling entire rooms with warmth and the smell of ozone. We'll see transistors replace those tubes, then watch those transistors shrink until billions of them fit on a chip smaller than your fingernail. We'll understand binary logic, the simple on and off that underlies all digital complexity. And we'll arrive eventually at artificial intelligence, machines that seem to think, built from nothing but silicon and mathematics. This will take time. We're in no hurry. If this story helps you rest tonight, feel free to like or subscribe, though there's no pressure, truly. I'm always curious where you're listening from, so if you feel like it, comment your city and what time it is there. It's oddly comforting to know that someone in Singapore is falling asleep at 3 a.m. while someone in Chicago settles in at 8 p.m. All of us connected through these same computers we're about to explore. Dim the lights now, if you haven't already. Adjust your pillow. Maybe turn on a fan for some gentle background noise, or let the silence settle around you. We have a long journey ahead, moving through centuries of invention and discovery, but we'll take it slowly, step by step, breath by breath. Let's begin. Before electronic computers, the age of mechanical calculation. Imagine you are standing in a counting house in Amsterdam in the year 1650. It's late afternoon, and the light coming through the tall windows has that golden quality of autumn. You can hear the scratch of quill pens on paper, the quiet murmur of clerks checking their arithmetic, the occasional sigh of frustration when a column of numbers doesn't balance. You're watching a merchant's accountant at work. He's been at this since dawn, calculating the value of a shipment of spices that arrived yesterday from the East Indies. He uses an abacus, his fingers moving the wooden beads with practiced precision. But even so, the work is slow. Each calculation must be checked and rechecked. A single error in the early morning could propagate through the entire day's work, turning profit into loss on paper, creating confusion that would take days to untangle. The room smells of ink and old paper, of the beeswax candles that will be lit soon as the daylight fades. The wooden floorboards creak occasionally as other clerks move between desks. Someone is sharpening a quill in the corner. You can hear the small scratching sound of the knife against the feather. The accountant rubs his eyes. He's been adding the same column 3 times, getting 3 different answers, and he's beginning to doubt his own ability to count. This is the world before computers. This is what calculation meant for most of human history. Slow, tedious, error-prone work done by hand and mind, hour after hour, day after day. The word computer originally meant a person who computed, someone whose job was to sit at a desk and perform arithmetic, filling ledger books with neat rows of figures, hoping not to make mistakes. Now imagine you move forward slightly in time to Paris in 1642. You're standing in a workshop that smells of metal polish and machine oil. Blaise Pascal, 19 years old, is demonstrating his Pascaline, a mechanical calculator housed in a wooden box about the size of a large book. The device is beautiful in its way, brass wheels with numbers engraved on them, gears that mesh with satisfying precision, a mechanism that can add and subtract through the simple act of turning dials. Pascal's father was a tax collector, spending his evenings doing exactly the kind of tedious arithmetic you just witnessed in that Amsterdam counting house. Young Blay decided to help him. The Pascaline represents hundreds of hours of thought and craftsmanship. Watch as Pascal demonstrates. He sets a number by turning the input wheels, then turns the operating handle. Inside the wooden case, you can hear the clicking of gears, the ratcheting of the carry mechanism moving from one column to the next. When he's finished, the answer appears in small windows at the top of the device. It works. It truly works. The answer is correct, achieved, without mental calculation, without possibility of arithmetic error, assuming the machine is properly built, assuming the gears are precisely cut, assuming everything is aligned just so. Touch the device. The brass is cool and smooth under your fingers. The clicking of the gears has a musical quality, almost hypnotic in its regularity. But here's the thing, the Pascaline never becomes popular. It's too expensive to manufacture, too delicate, too limited in its functions. Pascal builds perhaps 20 of them. Most are demonstration pieces, curiosities for wealthy collectors. The world of commerce continues with its clerks and abacuses and handwritten ledgers, calculating slowly, checking carefully, making errors, and correcting them. Time passes. You find yourself in London now, in the early 1800s. The Industrial Revolution is transforming the world around you. Steam engines are replacing water wheels. Factories are producing goods at scales previously unimaginable. And in a workshop cluttered with gears and brass plates and half-finished mechanisms, you watch Charles Babbage at work on his difference engine. Babbage is obsessed with accuracy. He's seen too many errors in mathematical tables, the logarithm tables that navigators use, the astronomical tables that predict the positions of planets. These tables are computed by human computers, transcribed by hand, typeset into books, and every step introduces potential errors. Ships navigate using faulty numbers. Astronomers base predictions on corrupted data. The problem haunts Babbage. His solution is mechanical, a machine that can calculate polynomial functions automatically, printing the results directly, eliminating human error from the process. The difference engine he's designing would be massive. Thousands of precision-machined parts, several tons of brass and iron, powered by a hand crank. You can see a portion of it on his workbench, gears meshing in columns, number wheels showing digits, the carry mechanism that would propagate changes from one column to the next. Pick up one of the gears. It's surprisingly heavy, cold metal, precision cut. The teeth are perfect. They must be perfect, or the entire machine would jam. Babbage is discovering that the vision is easier than the execution. The manufacturing capabilities of his era can barely meet the tolerances his design requires. Funding is unreliable. Political support wavers. The difference engine will never be completed in his lifetime, though a functioning version will eventually be built in the 20th century, proving that his mathematics were sound. But Babbage isn't finished. In the quiet evenings, working by candlelight, he's conceiving something even more ambitious. The analytical engine, a programmable mechanical computer that could, in theory, perform any calculation that could be expressed algorithmically. It would have memory, thousands of number wheels storing values. It would have a processing unit, the mill where calculations would occur. It would be programmed using punched cards, like those used in the Jacquard looms that were transforming the textile industry. You can see his drawings spread across the desk, mechanism after mechanism, each one a solution to a specific problem of automated calculation. The room smells of machine oil and coal smoke from the fireplace. The scratching of Babbage's pen fills the silence as he works through another calculation, designing machines that won't exist for a century, trying to build the future with brass and iron. Ada Lovelace, Lord Byron's daughter, will later describe the analytical engine's potential better than Babbage himself. It could compose elaborate pieces of music, produce graphics, solve equations, manipulate symbols according to rules. She will write what many consider the first computer program, a set of instructions for calculating Bernoulli numbers on a machine that will never be built. But the vision is there, clear and complete. Automatic calculation, programmable behavior, the mechanization of thought itself. The dream of computing before electronics is a dream of precision machinery, of gears and levers that never tire, never make mistakes, that calculate with the reliability of clockwork. But clockwork has its limits. Mechanical calculators can add and subtract efficiently enough, can even multiply through repeated addition, but they're expensive, delicate, limited. For complex calculations, solving differential equations, analysing statistics, predicting astronomical positions, teams of human computers remain more practical than machines. Imagine you're in an office at Harvard in the early 1900s, watching such a team at work. The Harvard computers, they're called, though the title refers to the people, not machines. Most are women, as computational work is considered appropriate for educated ladies, but beneath the dignity of male professors. They sit at wooden desks arranged in rows, each with paper, pencil, and perhaps a mechanical calculator, a more advanced descendant of Pascal's machine, able to multiply and divide through the turning of a hand crank. The room is filled with the sound of cranking, the clicking of gears, the scratch of pencils, the occasional quiet discussion as one computer checks another's work. They're calculating stellar positions, reducing astronomical observations to numbers, building tables that will be published in thick volumes. The work requires concentration and patience. A single error must be found and corrected. The numbers must be right. The head computer might spend years on this work, becoming expert in both mathematics and the peculiar art of organizing human calculation, deciding how to break complex problems into simpler steps, how to distribute work efficiently, how to check results for accuracy. It's intellectual work, demanding work, but it's slow. Computing the orbit of an asteroid might take weeks. Producing a comprehensive table of trigonometric functions might take years. You can smell the rubber erasers, the paper dust, the machine oil from the calculators. The light through the windows changes as the day progresses. Bright morning, warm afternoon, the golden quality of early evening. The computers work steadily, cranking their machines, writing down results, moving to the next calculation. This is computing in the early 20th century, still human, still mechanical, still slow. Though the technology has progressed from Babbage's never-completed engines, the fundamental limitation remains. Calculation is done by mechanisms that physically move, by gears that must turn, by wheels that must rotate. Speed is limited by inertia. Complexity is limited by the precision of manufacturing. And the dream of truly automatic computation, of machines that think, that solve problems independently, remains just that, a dream. But electricity is about to change everything. The birth of electronic computing, vacuum tubes, and room-sized machines. Now imagine you stand in a university laboratory, late 1930s. The building is cold, it's winter, though you'll soon find that this room is warmer than the others. You can hear a low hum, steady and electrical, coming from somewhere behind a partition. There's a smell in the air that's hard to describe if you've never encountered it. Ozone, that sharp, almost metallic scent that electricity produces when it arcs through air. And underneath that, the smell of warm electronics, dust heating on hot surfaces, the particular odour of vacuum tubes running at operating temperature. You round the partition and see it. Not one of the modern, sleek computers you might be imagining, but something that looks more like industrial equipment, or perhaps a telephone switching station. Tall metal racks reaching nearly to the ceiling, filled with vacuum tubes, hundreds of them, maybe thousands, each one glowing with a soft orange warmth from the filaments inside. They look almost like small light bulbs, or like the tubes in old radios, which is essentially what they are. Each one is generating heat, and collectively they're turning this room into something uncomfortably warm despite the winter outside. An operator in a white lab coat is working at a panel, flipping switches methodically, checking a diagram on a clipboard. Each switch connects or disconnects circuits, routing electricity through different paths, configuring the machine for a particular calculation. Programming this computer means physically rewiring it, or at least reconfiguring its switches and plugging patch cables into different sockets, like an old telephone switchboard, but instead of connecting voices, it's connecting logical operations. This is computing in the 1940s. This is ENIAC, the Electronic Numerical Integrator and Computer, though it might just as easily be Colossus in Britain, or one of the other pioneering electronic machines being developed in secret during and after World War II. Though your smartphone has incomparably more computing power in your pocket, these room-sized machines represent something revolutionary: electronic speed. No more gears and levers. No more mechanical delays. Just electricity flowing through circuits at a substantial fraction of the speed of light. Watch the operator work. She, and many of the operators, are women, continuing that tradition from the human-computer era, consults her programming sheet, flips a series of switches on one panel, then moves to another rack and plugs patch cables into a row of sockets. The cables are thick and stiff, colour-coded, each one carefully labelled. A mistake here could mean hours of debugging, or worse, could burn out expensive components. The work requires attention and care. Behind her, another technician is replacing a failed vacuum tube. They fail regularly, burn out like light bulbs, sometimes spectacularly, with a bright flash and a puff of smoke. With 18,000 vacuum tubes in ENIAC, something is always failing. The technician has a cart full of replacement tubes, organised by type, and a testing device to verify that the new tube works before installing it. He unscrews the failed tube, it's too hot to touch without protective gloves, sets it aside to cool, and screws in the replacement. The whole process has a routine quality, like changing a fuse or replacing a blown bulb. It happens multiple times per day. The room hums with electrical life. You can feel it, almost, that particular quality of high-voltage electricity flowing nearby, the slight static charge in the air, the warmth radiating from all those glowing tubes. Walk closer to one of the racks. The tubes are arranged in neat rows, and each one contains a delicate structure inside its glass envelope. A heated filament, like in a light bulb, and several electrodes. When the filament heats up, it releases electrons, tiny particles of electricity, and those electrons can be controlled by applying voltages to the other electrodes. Flow or no flow, current or no current, on or off. This is the fundamental insight that makes electronic computers possible. You can use electricity as switches, and switches can represent logic, and logic can represent computation. Each vacuum tube is a switch controlled by electricity rather than by hand. It can turn on or off thousands of times per second, far faster than any mechanical relay could operate, faster than any human could flip a switch. Chain enough of these tubes together in the right configuration, and they can add numbers, store values, compare quantities, make logical decisions, all at electronic speeds. But how? How does electricity become mathematics? Sit with this for a moment. Imagine a single tube glowing there in its socket. Electricity flows through it, or doesn't. On or off. 1 or 0. This is binary, the reduction of all complexity to the simplest possible distinction, the presence or absence of a signal. In the decimal system we use every day, we need 10 distinct states, 0 through 9. Mechanical calculators needed 10 positions on each number wheel, but electronic circuits work most reliably with 2 states, voltage present or voltage absent, current flowing or current stopped. So ENIAC and all the electronic computers that follow work in binary. A number like 5 isn't represented by a single tube showing 5. It's represented by a pattern of tubes being on or off, 1, 0, 1 in binary, which means one tube for the 4S place is on, one tube for the 2S place is off, one tube for the 1S place is on. Add them up, 4 plus 1 equals 5. Every number, every piece of data becomes a pattern of on and off, voltage and no voltage, electronic presence and absence. The operators finish their setup, one of them throws a large main switch, and you hear the electrical hum increase slightly as power flows to the computing circuits. Another checks a series of indicator lights, small bulbs that show the status of different components, glowing in patterns that mean something to her, but look nearly random to you. She nods, satisfied. The machine is ready. They feed in the problem, not by typing on a keyboard, which won't become common for years yet, but by setting switches and dials, entering numbers in binary through physical controls. Then they start the calculation sequence. Relays click as circuits activate and deactivate. The indicator lights flicker in complex patterns. Deep in the racks of tubes, electricity is flowing through carefully designed paths, through circuits that add and multiply and compare, implementing the logical operations that will eventually produce an answer. It takes time. Not hours like the human computers required, not even minutes, but seconds, long enough that you can hear the clicking of relays, see the flicker of lights, sense the machine working its way through the problem. And then, the output, a pattern of lights, or numbers printed on a tape, or values stored in the machine's memory circuits to be read out later. The answer. Correct, assuming everything is wired properly, assuming no tubes have failed mid-calculation, assuming the binary to decimal conversion is done properly. ENIAC's first calculation, if you're curious, wasn't for artillery tables as originally intended. The war had ended. Instead, scientists from Los Alamos used it to perform calculations for the hydrogen bomb project, a fact that sits uneasily in history, this marriage of pure mathematics and pure destruction. The machine, indifferent to the meaning of its calculations, simply computed, performing in seconds what would have taken human computers months or years. But let's step across the Atlantic for a moment. Imagine you're now in Bletchley Park, Britain, during the war years, though you wouldn't have been allowed in here then, not without the highest security clearance. In a hut that looks unremarkable from outside, another electronic computer is humming. Colossus, built to break German codes, to find the patterns in encrypted messages that would reveal military secrets. Colossus is earlier than ENIAC, operational in 1943, making it arguably the first programmable electronic digital computer, though the debate continues among historians. It has fewer tubes than ENIAC, only about 2,500 in the Mark I version, but it's faster for its specific purpose. And that purpose is pattern matching, reading encrypted messages from punched paper tape, performing statistical analyses at speeds no human team could match, finding the tiny correlations that reveal the encryption key. The machine reads tape at 5,000 characters per second. an astonishing speed for the era. You can hear it, the tape running through the optical reader, a soft rushing sound, and the clicking of photoelectric cells converting the holes in the tape to electrical pulses. The pulse patterns flow through the vacuum tube circuits, are compared against stored patterns, produce counts and correlations that the cryptanalysts use to break each day's codes. The engineers who built Colossus, Tommy Flowers chief among them, had to solve problems no one had encountered before. How do you make circuits that can count at kilohertz speeds? How do you store numbers temporarily, remember them while performing comparisons, then update them based on results? How do you build something reliable enough to run for hours or days without stopping, despite using thousands of components that frequently fail? They solved these problems through clever circuit design, through redundancy, through careful engineering. And through secrecy, Colossus's existence remained classified until the 1970s, so it couldn't influence the public development of computers for decades. Whether ENIAC or Colossus deserves the title of first computer depends on how you define the terms. First programmable, first general purpose, first to use a stored program. The distinctions matter to historians and engineers, but perhaps less to us, drifting through these memories on our way to sleep. What matters is the transition they represent, from mechanical to electronic, from human speed to electrical speed, from calculation as patient human labour to calculation as the flow of electrons through circuits. Time passes. You find yourself now in the early 1950s in a university computer laboratory that smells of ozone and warm electronics and the particular industrial odour of military-grade electrical equipment. The computers have names now: UNIVAC, EDSAC, Mark I at Manchester. They still fill rooms, still require teams of operators and technicians, still consume kilowatts of power and generate enough heat to be uncomfortable even in winter. But they've evolved. The programming has changed. Instead of rewiring the machine for each problem, these computers can store their programs in memory as patterns of bits, just like data. This is the von Neumann architecture, named after John von Neumann, though others contributed to the concept. A computer with memory that stores both instructions and data, with a central processing unit that fetches instructions, decodes them, executes them in sequence. The program becomes data, the distinction blurs, the machine becomes truly general purpose, capable of performing any calculation that can be expressed as a sequence of instructions. Watch the morning routine. An operator arrives early, begins the warm-up process. Vacuum tubes need time to reach operating temperature. Switching on a cold computer risks thermal stress that could crack the glass envelopes or damage the delicate internal structures, so she activates the heaters, waits for the tubes to glow orange, watches the voltage indicators climb to their proper levels. The room gradually warms. The electrical hum increases. After perhaps 20 minutes, the machine is ready. She loads the program, a stack of punched cards, each one representing an instruction or a piece of data, holes punched in precise patterns that will be read by mechanical sensors and converted to electrical signals. The card reader clacks as it pulls in each card, reads it, moves to the next. The program loads into memory patterns of voltage stored in mercury delay lines or on the surfaces of cathode ray tubes, or in arrays of vacuum tubes configured as flip-flops, each storing a single bit. Then the computation begins. The CPU fetches the first instruction from memory, decodes it, add these two numbers, or jump to a different instruction if a certain condition is true, or store a value in memory, executes it, moves to the next. The process repeats at speeds that seem miraculous compared to human calculation. thousands of operations per second, with each operation completed correctly, deterministically, reliably, or usually reliably. Sometimes a tube fails mid-calculation, or sometimes a bit of dust interferes with the card reader. Sometimes cosmic rays, high-energy particles from space, strike the memory circuits and flip a bit from 0 to 1 or 1 to 0, corrupting data in a way that won't be well understood for decades. The operators learn to recognize the symptoms, programs that hang, results that make no sense, the telltale flicker of error lights. They restart, reload, try again. But despite the failures, despite the maintenance requirements, despite the heat and the noise and the expense, these early electronic computers prove their worth. They calculate faster than any alternative. They solve problems that would be practically impossible for human computers, simulating nuclear reactions, predicting weather patterns, optimizing airline schedules, modeling fluid dynamics. Science and engineering and business all start to reorganize around these new capabilities. And beneath it all, the same fundamental mechanism, electricity flowing through circuits, tubes turning on and off, binary patterns representing numbers and instructions, and eventually everything digital, text and images and music and video, all reduced to sequences of ones and zeros, all processed by electronic switches operating at speeds the mechanical era could never achieve. But vacuum tubes have their limits. They burn out too frequently, they consume too much power, they generate too much heat, they're too large, you can fit only so many into a room before heat and power requirements become unmanageable. For computers to become more powerful, more reliable, more accessible, something else is needed. That something is being developed right now in laboratories at Bell Labs in a search for a better component for telephone switches. It's smaller than a pea, uses almost no power, generates almost no heat, will last for decades without failure. It's called a transistor. Understanding binary, logic, how on and off becomes everything. But before we move forward to transistors, let's pause here in this warm room full of glowing vacuum tubes and understand what's really happening at the most fundamental level. Because everything that follows, every computer you've ever used, every smartphone, every server processing your web searches, every artificial intelligence, builds on these same basic principles. Imagine you're watching a single circuit, a single vacuum tube glowing there in its socket. You can control it. Apply a voltage to one electrode and current flows through the tube, lighting an indicator bulb. Remove the voltage and the current stops. The bulb goes dark. On or off. 1 or 0. True or false. The simplest possible switch, controlled by electricity instead of by hand. Now imagine two tubes arranged in a specific way. The output of both tubes connects to a single indicator. The indicator lights only if both tubes are on, if current flows through both. This is an AND gate. It outputs true only if both inputs are true. If tube A is on and tube B is on, then the output is on. Otherwise, the output is off. Picture it differently if that helps. Two water valves in series, one after the other in a pipe. Water flows through only if both valves are open. Close either valve and the flow stops. It's the same logic whether implemented with water or electricity or dominoes falling or any other medium that can have two distinguishable states. Now imagine a different arrangement, two tubes whose outputs connect in parallel to an indicator. The indicator lights if either tube is on, if current flows through either path. This is an OR gate. It outputs true if either input is true. If tube A is on, OR tube B is on, or both, then the output is on. Only if both are off does the output stay off. And one more, even simpler, a single tube arranged so that it inverts the signal. When you apply voltage to activate it, the output goes low. When you remove the voltage, the output goes high. This is a NOT gate, an inverter. It outputs the opposite of its input. True becomes false. False becomes true. 1 becomes 0. 0 becomes 1. These three logical operations, and, or, not, are sufficient to implement any possible logical function, any computation, any algorithm. They're the atoms of digital logic, and everything else builds from them. Let that settle for a moment. Three simple operations combined in various ways can create all the complexity of modern computing. Let's see how. Imagine you want to add two binary numbers. Take the simplest case, adding two single bits. The possible inputs are 0 plus 0, 0 plus 1, 1 plus 0, or 1 plus 1. The outputs are 0, 1, 1, or 10, which is 2 in binary, 1 in the next column, 0 in this column, so you get a sum bit and a carry bit. You can implement this with logic gates. An XOR gate, exclusive or true, if one input is true but not both, gives you the sum bit. An AND gate gives you the carry bit. Wire them together appropriately and you have a half adder, a circuit that adds 2 bits. Connect multiple half adders with some additional logic to handle the carry from one column to the next, and you have a full adder. Chain multiple full adders together and you can add numbers of any length. 8-bit, 16-bit, 32-bit, whatever you need. Inside those vacuum tube computers, inside the transistors that will follow, inside every CPU ever made, the arithmetic circuits work exactly this way. Chains of logic gates, carefully arranged, each one performing its simple operation, the results cascading through layers of logic until the final answer emerges. Addition is just the beginning. Multiplication is repeated addition. Division is repeated subtraction. Complex functions are decomposed into simpler operations until you reach operations that can be implemented with basic gates. The beauty of it, and perhaps this is a strange word to use, but it's true, the beauty of it is the simplicity underlying the complexity. You could, if you had patience and sufficient components, build a working computer from light switches and light bulbs. It would be slow, absurdly slow, but it would work. Each light switch would be a bit. Each bulb would show an output. And by wiring them together correctly, you could implement logic gates, then adders, then memory, then a complete processor. Computer engineers in the vacuum tube era understood this deeply. They designed circuits by hand, drawing logic diagrams on paper, working out the signal paths, calculating delays, ensuring that signals would arrive synchronized at the right places at the right times. A typical adder circuit might use dozens of tubes. A multiplier might use hundreds. A complete computer, thousands. And yet it all reduces to patterns of on and off, voltage present and voltage absent, electricity flowing or not flowing through carefully arranged circuits. The numbers being computed have no meaning to the circuits themselves. A pattern of bits might represent a number, or a letter, or an instruction, or a pixel color, or a sound sample. The circuits don't care, they just perform their logical operations, transforming input patterns to output patterns according to fixed rules. Let's go deeper. How do you store a number? How do you remember a value so you can use it later in a calculation? You create a circuit that holds a state, a flip-flop, 2 tubes wired so that they form a stable loop. Set one tube on and the other off, and they'll stay that way, remembering one bit. Set them the opposite way, and they remember a different bit. Chain these together, and you have a register, a place to store a multi-bit number temporarily. For larger memory, the vacuum tube computers used various clever techniques. For large memory, mercury delay lines send an electrical pulse through a tube of mercury, let it bounce back and forth, detect it as it passes a sensor, refresh it by sending it through again. The pulse travels at the speed of sound in mercury, much slower than electrical signals in wires, giving you time to store hundreds or thousands of bits in a single tube. But it's sequential. You have to wait for the right pulse to come around, and it's temperature sensitive. The speed of sound in mercury changes with temperature, requiring careful calibration. Or cathode ray tubes, like television picture tubes. A beam of electrons scans across a phosphorescent screen, and you can detect whether each spot on the screen is charged or uncharged, storing 1 bit per spot. These were faster than mercury delay lines, more random access, but temperamental and limited in capacity. Or magnetic cores, tiny ferrite rings that could be magnetized clockwise or counterclockwise, storing 1 bit each, arranged in grids of thousands or millions, robust and reliable, but expensive to manufacture. Core memory will become dominant in the transistor era, but in the vacuum tube era it's still being developed. The point is that every bit, every 1 or 0, exists somewhere physically. As a tube on or off, a pulse travelling through mercury, a charged spot on a phosphor screen, a magnetized core. Information is always physical, computation is always a physical process. The logic may be abstract, the algorithms may be mathematical, but they execute through the flow of electricity and the switching of components and the storing of states in physical media. Imagine you're watching a computation in slow motion, slowed down enough that you can see each step. An instruction is fetched from memory, a pattern of bits representing add register A to register B. The pattern flows to the control unit, which decodes it, activating the appropriate circuits. The values in registers A and B flow to the adder circuit. The carry bits propagate from one column to the next. The result emerges and flows back to register B, overwriting what was there before. The program counter increments, pointing to the next instruction. The cycle repeats. Each of these steps happens through the coordinated switching of dozens or hundreds of vacuum tubes, each turning on or off at exactly the right time, controlled by carefully designed timing circuits that generate clock pulses to synchronize everything. The clock might tick thousands of times per second in these early machines, far slower than the gigahertz clocks of modern processors, but fast enough to be useful, fast enough to be revolutionary. And all of this is binary. The numbers, the instructions, the addresses, the control signals, everything is patterns of 1s and 0s, voltage present or absent. There is no 3. There is no maybe. There is no ambiguity. The digital world is discrete, quantized, fundamentally simple in its logic, even when complex in its behavior. This is what makes digital computers so different from analog computers, devices that represent numbers as continuous voltages or shaft rotations, measuring rather than counting. Analog computers can be fast and elegant for certain problems, but they're limited by the precision of their components, by noise and drift, by the difficulty of storing and reproducing exact values. Digital computers built from switches that are clearly on or clearly off can achieve arbitrary precision by using more bits, can store values indefinitely without degradation, can reproduce calculations exactly. The future of computing is digital. The future is binary. The future is built on the simple foundation of on and off, repeated billions of times, organized into layers of increasing abstraction until simple becomes complex, until patterns become meaningful, until switches become intelligent. But we're getting ahead of ourselves. Until switches, we're We're still in the vacuum tube era, in rooms warmed by glowing orange tubes, listening to the hum of power transformers and the clicking of relays. The computers are progressing, becoming more capable, but they're still rare, still expensive, still temperamental. For computing to truly transform the world, it needs to become smaller, cheaper, more reliable. It needs the transistor. The transistor revolution, when computers started shrinking decades past. It's December 1947 now, and you find yourself at Bell Laboratories in Murray Hill, New Jersey. Outside it's cold, winter settling over the northeastern United States. Inside, in a small laboratory, 3 men are working with equipment that looks almost crude: a microscope, some fine wire, a small piece of germanium crystal mounted on a metal base. John Bardeen, Walter Bratton, and William Shockley are searching for a solid-state replacement for vacuum tubes, a component for telephone switches that doesn't need warm-up time, doesn't burn out after hundreds of hours, doesn't consume significant power, or generate heat. They're exploring semiconductors, materials like germanium and silicon that conduct electricity better than insulators but worse than metals, and whose conductivity can be controlled by adding impurities or applying electric fields. Watch as Bratton works under the microscope. He's positioning 2 fine gold wires, barely separated, pressed against the surface of a germanium crystal. The crystal has been carefully prepared, its surface oxidized in specific ways, the atomic structure altered by controlled contamination with other elements. This is delicate work. The spacing between the wires matters at the scale of micrometers. He applies voltage. Current flows through one wire into the germanium and comes out through the other wire. But not just any current. The small current flowing into one wire controls a larger current flowing through the other. It's amplification. It's switching. It's the electronic equivalent of a vacuum tube, but built from solid materials with no moving parts, no vacuum envelope, no heated filament. It works. It actually works. They spend days verifying, testing, understanding what they've created. By late December, they're confident enough to demonstrate it to Bell Labs management. The device is called a point contact transistor, transistor being a blend of transfer resistor, describing how it transfers signals between circuits of different resistance. Touch the device. It's tiny, the size of a pencil eraser, far smaller than even the smallest vacuum tube. It's cool. When operating, it barely warms. It requires milliwatts instead of watts. It should last for years, potentially decades, with no consumable parts to burn out. It represents the future, though few people realize it yet. The transistor will win the 3 inventors the Nobel Prize. It will be called the most important invention of the 20th century, and within a few years it will begin replacing vacuum tubes in everything: radios, hearing aids, telephone switches, and eventually computers. But the transition takes time. Early transistors are expensive, individually handcrafted. They're less reliable than vacuum tubes in some ways, more sensitive to temperature, to voltage spikes, to manufacturing variations. And the engineering community knows vacuum tubes. There are established design practices, proven circuits, trained technicians. Switching to a new technology means abandoning that expertise, learning anew. Time moves forward. You find yourself now in the mid-1950s in a clean, bright laboratory where engineers are working with transistorized circuits. The transistors have evolved. Point contact types have given way to junction transistors with better performance and reliability. Germanium is being replaced by silicon, which works at higher temperatures. Manufacturing processes are improving, costs are falling, and engineers are learning to design transistor circuits that are faster, more powerful, more sophisticated than vacuum tube equivalents. See that computer prototype in the corner? It's the TX0 built at MIT, one of the first fully transistorized computers. It uses 3,600 transistors, where a vacuum tube machine would have used thousands of tubes. It fits in a single room, not a warehouse. It's air-conditioned, not because the electronics require cooling, but for human comfort. The power requirement is a tenth of what a tube machine would need. And it's reliable, days or weeks of continuous operation between failures, not hours. The technician opens a panel showing you the inside. The transistors are mounted on circuit boards, each one a tiny cylinder of metal about the size of a grain of rice with 3 wire leads. They're soldered in place alongside resistors and capacitors and other components, forming circuits that implement logic gates, registers, memory interfaces. The boards are clean, organized, nothing like the tangled nests of wires in vacuum tube machines. There's a faint smell of solder and circuit board resin, but none of the ozone and hot vacuum tube smell of the earlier era. The machine runs. You can barely hear it, a soft hum from the power supply, the whir of a cooling fan, the mechanical clicking of the paper tape reader. No clicking relays, no crackling tubes. Just quiet electronic computation, signals flowing through solid-state components at speeds that exceed anything vacuum tubes could manage. The transistor's switching time is measured in microseconds, or faster, limited by physics rather than by thermal inertia. Programs that would have taken hours on vacuum tube machines now take minutes. The computer can be turned on instantly with no warm-up period. And it's small enough, reliable enough, economical enough that universities can afford their own computers instead of sharing time on large institutional machines. Computing is beginning to democratize. But more importantly, the transistor opens possibilities that vacuum tubes never could. Because transistors are small, you can pack more of them into the same space, creating more complex circuits. Because they're reliable, you can build systems with millions of components instead of thousands. Because they use little power, you can put computers in places that couldn't support the electrical and cooling requirements of tube machines. The transistor doesn't just replace the vacuum tube, it transforms what computing can be. Imagine you're now in a factory in the early 1960s watching transistor radios being manufactured. The assembly line moves steadily, circuit boards populated with components, transistors soldered in place, cases assembled, speakers connected. These radios are small enough to fit in a pocket, portable, battery-powered, none of which would have been remotely feasible with vacuum tubes. They cost a few dollars instead of a few dozen. Millions are being produced, mostly in Japan, where companies like Sony and Panasonic have mastered high-volume transistor manufacturing. This is the first wave of ubiquitous electronics. Before transistors, electronics meant furniture-sized items, console radios, television sets, mainframe computers. After transistors, electronics can be personal, portable, embedded everywhere. The transistor radio is just the beginning. Soon there will be transistorized televisions, calculators, hearing aids, guitar amplifiers, test equipment, a proliferation of devices that all build on the same basic component. And in computer laboratories around the world, engineers are pushing further. Computers are shrinking from room size to closet size to desk size. They're becoming faster, more capable, more affordable. Universities, research institutions, large companies are buying them, using them for calculations that were impossible before. Programming is evolving from machine code written in binary to assembly language with symbolic names to early high-level languages like Fortran and COBOL that let programmers express algorithms more naturally. The morning routine has changed. An operator arrives, flips a power switch, and the computer boots almost immediately. No waiting for tubes to warm up. She loads a program from magnetic tape or from punched cards. The program runs, producing results printed on continuous feed paper or stored on more magnetic tape. The room stays comfortable. The machine runs quietly. When something fails, which happens far less often than in the vacuum tube era, a technician replaces a small circuit board rather than hunting for burned-out tubes. The smell of the computer room has changed too. Less ozone and hot electronics, more the smell of paper and magnetic tape, and the particular odour of electronics cooling fans, moving air over components that barely need cooling, but getting it anyway for reliability. The lighting is ordinary fluorescent tubes, not the orange glow of vacuum tubes reflected on metal panels. Remember ENIAC's 18,000 hot vacuum tubes filling a room? A single transistor does the same job, cold and silent. The comparison is almost absurd. And yet even in this era of transistorized computers, the machines remain specialized, expensive, maintained by professionals in climate-controlled rooms. They're tools for institutions, not individuals. For computing to become truly personal, for computers to appear in homes and schools, and small businesses, another revolution is needed. The transistor made computers smaller and more reliable, but millions of individual transistors, each one separately manufactured and soldered into place, still impose limits on complexity and cost. What's needed is integration, a way to build not just one transistor, but dozens or hundreds or thousands or millions of transistors, all fabricated together as a single component, connected together with microscopic wires that never need soldering, assembled by processes that scale efficiently from dozens to billions. What's needed is the integrated circuit, the microchip, the foundation of everything digital that will follow. But that story will have to wait. We've covered decades now, moved from Babbage's brass gears through glowing vacuum tubes to tiny transistors. We've watched computers shrink from warehouse-filling behemoths to room-sized machines to desk-sized systems. We've seen them become faster, more reliable, more accessible. We've understood how binary logic and switching circuits transform electricity into calculation. The journey continues, but you've travelled far already tonight. The circuits rest now. Or rather, they never rest, electrons flowing endlessly through silicon pathways, computing through the night while the world sleeps. Integrated circuits and microchips. Computing gets, microscopic time moves forward. Imagine you stand in a clean room, 1961. But this isn't like any room you've been in before. You're wearing a full-body suit, white, hooded, covering everything but your eyes. The air smells sterile, almost nothing, filtered and recirculated hundreds of times per hour. The lighting has a strange yellow quality, carefully chosen not to expose the photosensitive materials being processed here. You're at Fairchild Semiconductor in California, watching the birth of something revolutionary, the integrated circuit. Jack Kilby at Texas Instruments and Robert Noyce here at Fairchild have independently realized something profound. Instead of building circuits from individual transistors soldered onto boards, you can fabricate dozens or hundreds of transistors together on a single piece of silicon, connecting them with microscopic metal pathways that are part of the manufacturing process itself. Watch the engineer at the microscope. She's examining a silicon wafer, a thin disc about the size of a small coin in these early days, though they'll grow much larger. The surface is mirror smooth, polished to near perfection. On this surface, through a series of chemical processes, dozens of identical circuits have been created, each one containing multiple transistors, resistors, capacitors, all interconnected. The process is almost magical in its precision. The silicon wafer starts pure, then gets coated with photoresist, a light-sensitive chemical. A photomask, like a stencil made of glass with opaque patterns, is placed over the wafer. Ultraviolet light shines through the transparent parts of the mask, exposing the photoresist underneath. The exposed photoresist is washed away, leaving a pattern. Then chemicals etch the exposed silicon, or other materials are deposited, building up layers. The process repeats: coat, expose, develop, etch or deposit, over and over, each step adding another layer of the circuit. Touch the wafer, carefully, at the edges only. It's cool, smooth as glass, because essentially it is glass, or rather crystalline silicon. But on its surface, invisible to your naked eye, are structures measured in micrometers. Tiny transistors, thin metal traces connecting them, insulating layers separating different levels of circuitry. An entire circuit that would have required a breadboard full of components now fits in a space smaller than your fingernail. This is the integrated circuit, and it changes everything. The first ICs are simple. Perhaps 10 transistors, a few logic gates. But the potential is obvious. If you can integrate 10 transistors, why not 100? Why not 1,000? The only limits are the precision of your manufacturing and the size of your silicon wafers. The clean room is crucial. A single speck of dust landing on the wafer during processing can ruin an entire circuit. The air is filtered to remove particles larger than a few micrometers. Workers wear the bunny suits to prevent skin cells and hair and clothing, fibers, from contaminating the process. Everything is controlled: temperature, humidity, air pressure, vibration. You can hear the soft, constant hum of the laminar airflow system, pushing filtered air from ceiling to floor in smooth, non-turbulent streams. Time passes. You find yourself now in the early 1970s at Intel's fabrication facility. The wafers have grown, 4 inches in diameter now, soon to be 6. The feature sizes have shrunk. Transistors that were 10 micrometers across in the early days are now just a few micrometers. Each wafer contains hundreds of chips. Each chip contains thousands of transistors. Gordon Moore, one of Intel's founders, has observed something that will become famous as Moore's Law. The number of transistors you can fit on a chip seems to double approximately every 2 years. It's not a physical law like gravity. It's an observation about the pace of engineering progress, about how the semiconductor industry improves its manufacturing precision, shrinks its features, grows its wafers, optimizes its processes, and remarkably, it will hold true for decades. Watch the manufacturing line. Wafers move through station after station, coating, exposure, development, etching, ion implantation, shooting atoms into the silicon to change its electrical properties, deposition, planarization, polishing layers perfectly flat. Each wafer might spend weeks working its way through the process, with dozens or hundreds of individual steps. A modern chip isn't built in 2 or 3 layers. It might have 10, 20, eventually hundreds of layers, each one precisely aligned to the ones below. At the end of the process, the wafer is tested. A probe card, a bed of tiny needles, touches each chip on the wafer, applying signals, measuring responses, identifying which chips work and which have defects. Not all chips survive manufacturing. Dust, slight variations in process conditions, imperfections in the starting silicon can all cause failures. The good chips are marked. The bad ones are noted but left in place. Then the wafer is cut, diced with a precision diamond saw into individual chips. The good chips are mounted in packages, ceramic or plastic housings, with metal pins that can be soldered into circuit boards. The pins connect to the chip through thin gold wires bonded with ultrasonic welding to pads on the chip's surface. Each wire is finer than a human hair, carrying signals between the silicon and the outside world. The smell in the assembly area is different from the clean room: warm plastic from the packaging process, a slight chemical odour from the moulding compound, the faint ozone smell of the wire bonding equipment. Workers, this part is still done largely by hand in this era, carefully position chips, bond wires, seal packages. It's precise, patient work requiring steady hands and good eyes. You watch the routine repeat through the day: chip placement, wire bonding, visual inspection under magnification, package sealing, marking, testing. Each packaged chip goes through functional tests, signals applied to the pins, responses measured, pass or fail determined in seconds. The passing chips go into tubes or trays, ready for shipment to computer manufacturers, calculator companies, the growing electronics industry that's building the digital age component by component. The engineers in these facilities spend their days solving problems that didn't exist a decade earlier. How do you prevent static electricity from damaging chips so small that a few stray electrons can destroy them? How do you automate testing when each chip type requires different test patterns? How do you cool chips that generate more heat as they grow more complex? The solutions are practical, incremental: anti-static wrist straps, automated test equipment, heat sinks made of aluminum or copper, thermal paste to improve heat transfer. In the design rooms, separate from the clean manufacturing areas, engineers work with new tools, computer-aided design systems that let them draw circuits on screens instead of on paper, simulation software that predicts how designs will behave before manufacturing, layout programs that arrange thousands of components and route the connections between them. The computers designing computers, a recursive loop that will accelerate progress in ways that seem almost impossible. These integrated circuits are appearing in everything. Calculators that once required dozens of transistors now use single chips. Watches are going electronic, with chips replacing mechanical movements. Computers are becoming more powerful and compact as boards full of individual transistors are replaced by boards with just a few ICs, each IC doing the work of dozens or hundreds of discrete components. But the most important integrated circuit hasn't arrived yet. Engineers can build chips with thousands of transistors now, and someone, somewhere, is going to realize that you could put an entire computer's central processing unit on a single chip. Not the memory, not the input and output interfaces, but the brain, the processor that fetches and executes instructions, could fit on one piece of silicon. That chip is coming. It's called a microprocessor, and it will make personal computing possible. The microprocessor, a computer on a chip. You find yourself watching a demonstration at Intel, late 1971. The engineer is holding something smaller than a postage stamp. The Intel 4004, the first commercial microprocessor. It contains 2,300 transistors. Remember when computers needed thousands of vacuum tubes, each the size of a light bulb? Now those thousands of switches fit on a chip you could lose in your pocket. The 4004 was designed for calculators, but it's actually a general-purpose computer. It can fetch instructions from memory, decode them, execute them, store results. It has registers to hold data temporarily, an arithmetic logic unit to perform calculations, a control unit to orchestrate everything. It's a complete CPU, capable of running programs, just extraordinarily simple compared to what will come later. The chip runs at 740 kHz, less than 1 million cycles per second, glacially slow by modern standards, but fast enough for its time. It processes data 4 bits at a time, working with tiny numbers, but it's programmable. Give it the right sequence of instructions in its memory, and it will execute them faithfully, performing whatever task you've encoded. Time shifts. You're now in 1975 in a garage in Albuquerque, New Mexico. The air smells of solder and coffee. 2 young men, Paul Allen and Bill Gates, are writing software for the Altair 8800, a kit computer built around the Intel 8080 microprocessor, a more powerful successor to the 4004, with 6,000 transistors processing 8 bits at a time, running at 2 MHz. The Altair itself is a metal box with switches on the front panel and rows of LED lights. It has no keyboard, no screen. You program it by flipping switches to enter binary instructions and read the results from the pattern of lights. It's primitive, absurdly so, but it's also affordable. For less than $400, a hobbyist could own a real computer, not time-sharing on a mainframe, not borrowing time at a university, but a computer of their own. The hobbyist computer movement is exploding. Electronics magazines publish circuit diagrams. Clubs form. The Homebrew Computer Club in Silicon Valley becomes legendary, a place where enthusiasts share designs, trade components, dream about what's possible now that the CPU is just another chip you can buy. Steve Wozniak designs the Apple One in his spare time, selling boards to other club members. Steve Jobs sees the potential for a complete product, not a kit but a finished computer, and the Apple II follows. Imagine you're at a kitchen table now, late 1970s. An Apple II sits there, beige plastic case, built-in keyboard, connected to a television as a display. It's running. You can hear the quiet whir of its cooling fan, smell the warmth of the power supply. The screen glows green. Monochrome phosphor, not the colour displays that will come later for those who can afford them. Someone is programming in BASIC, typing commands that appear on the screen. The keyboard clicks with each key press, a satisfying mechanical sound. They're writing a simple program, maybe to calculate something, or to display a pattern, or to play a primitive game. When they run it, the computer executes their instructions, showing results on the screen almost instantly. It's interactive, immediate, personal, in a way that batch processing mainframes never were. The smell of these early personal computers is distinctive. Warm electronics and plastic, the slight ozone from the power supply, sometimes the rubber of the keyboard keys. The floppy disk drives, when someone can afford to add them, make wonderful mechanical sounds, clicking and whirring as they spin the magnetic disks and position the read/write heads. Loading a program from a cassette tape is even more visceral. You can hear the audio tones, the beeps and warbles that represent data as the computer decodes them back into binary. These early microprocessors are simple compared to what will come, but they're enough to run spreadsheet programs that will revolutionize business accounting, enough to run word processors that will replace typewriters, enough to run games that will capture imaginations, enough to prove that computers don't need to be institutional resources. They can be personal tools, creative instruments, windows into a digital world. How CPUs actually work. Inside the silicon. But let's pause again and understand what's happening inside that microprocessor chip. Imagine you could shrink down and watch it work. The chip is mostly silicon, a semiconductor, neither conductor nor insulator, but something in between. Through careful doping, adding tiny amounts of other elements, the silicon's electrical properties are modified in specific places, creating regions that conduct differently. Transistors are built from these regions. Each transistor is essentially 3 regions of silicon, 2 that can conduct, source and drain, separated by a channel that's normally non-conducting. Above the channel is a thin insulating layer, and above that a metal gate. When you apply voltage to the gate, it creates an electric field that changes the channel, making it conduct. Remove the voltage and the channel stops conducting. It's a switch controlled by electricity built from nothing but silicon and metal traces. Chain these switches into logic gates. And, or not, all the operations you learned about earlier with vacuum tubes. Chain those gates into larger blocks. Adders that can add numbers, multipliers, comparators that can test if one number is larger than another. Organize those blocks into functional units. The arithmetic logic unit that performs calculations, the control unit that decodes instructions and orchestrates everything, registers that store values temporarily. The chip operates in cycles, synchronized by a clock, an oscillator that generates a regular electrical pulse. On each clock pulse, things happen. Instruction fetch, decode, execute, write back. The cycle repeats billions of times per second in modern processors, but even in these early microprocessors, it's happening thousands or millions of times per second. Imagine watching a single instruction execute in slow motion. The program counter, a register that holds the address of the next instruction, sends its value to the memory interface. The memory returns the instruction, a pattern of bits that means something like add register A to register B. This pattern flows to the instruction decoder, which activates control signals that open specific pathways through the chip. The values from registers A and B flow to the ALU, where transistors configured as adder circuits produce the sum. The result flows back to register B, overwriting what was there. The program counter increments, pointing to the next instruction. All of this happens through the coordinated switching of thousands of transistors, signals propagating through layers of logic at nearly the speed of light in silicon. The paths are measured in micrometers, the signals are measured in volts, the timings are measured in nanoseconds. It's precise, deterministic, reliable. The same inputs always produce the same outputs. Modern processors add complexity to increase performance. Cache memory that stores frequently used data close to the CPU, pipelining that lets multiple instructions be in different stages of execution simultaneously, branch prediction that guesses which way a program will go and prepares ahead of time. But the fundamentals remain the same. Fetch, decode, execute billions of times per second, binary logic turning electricity into computation. Personal computing takes over. The 1980s and 1990s, time moves forward. You find yourself in an office, mid-1980s. The IBM PC sits on the desk, beige metal case, separate monitor with green or amber phosphor, mechanical keyboard that sounds like distant thunder when someone types quickly. It's running DOS, Microsoft's disk operating system, showing a simple command prompt, C:\\, greater than the office smells of coffee and paper and the warm electronics of the computer. The PC's fan hums steadily. When the hard drive accesses data, and hard drives are still uncommon enough to be notable, you can hear it, the whir of the disk spinning, the click of the read heads positioning themselves. 20 megabytes of storage, enormous for its time, though you'll later marvel that a single photo can exceed that. DOS is text-based. You type commands, the computer responds with text. It's powerful but not intuitive, requiring memorization of commands and syntax. But it's enough. Lotus 123, the spreadsheet program, is transforming how businesses work. VisiCalc before it proved the concept, but Lotus 123 on the IBM PC becomes the standard. Accountants who spent days with calculators and ledger books now complete the same work in hours. WordPerfect, WordStar, and later Microsoft Word are replacing typewriters. The ability to edit before printing, to save and revise documents, to copy and paste text. These seem like small things, but they change how people write, how businesses operate, how ideas are developed and shared. Across the room, someone is using an Apple Macintosh. It's 1984, and the Mac is revolutionary. A graphical user interface with windows and icons and a mouse, making the computer intuitive enough that people can learn by exploration rather than by reading manuals. You can hear the distinctive sound of the Mac's single 3.5-inch floppy drive as it loads the system, a mechanical clicking and whirring that becomes familiar to millions. The Mac's screen is small, 9 inches, black and white, but sharp and clear. The mouse is a revelation for those who've never used one. Moving it on the desk moves a cursor on the screen, clicking selects things, dragging moves them. It's direct manipulation, a more natural way to interact with the computer than typing cryptic commands. Through the late 1980s, computers spread through offices. The distinctive sounds of dot matrix printers become ubiquitous. The high-pitched whine of the motor, the rhythmic impact of pins against paper, the grinding as the print head moves back and forth. The paper is continuous feed, perforated pages connected by strips with sprocket holes, tearing apart with a satisfying rip when a print job finishes. Microsoft Windows arrives, bringing graphical interfaces to IBM PC compatibles. Early versions are clunky, but they improve with each release. Windows 3.0, then 3.1, become genuinely usable, and suddenly the IBM PC world has something approaching the Mac's ease of use, while maintaining compatibility with the vast library of DOS software. The morning routine in offices changes. Arrive, turn on the computer, wait through the boot sequence, the beeps and whirs and disk accesses that mean the system is loading. Check email, though email is still mostly internal to companies, not yet the universal communication medium it will become. Work in spreadsheets or word processors through the day, saving frequently because systems still hang occasionally, still crash, still lose work if you're not careful. The smell of computers becomes familiar. Warm plastic and electronics, the particular odour of CRT monitors, cathode ray tubes like televisions, with their slight electrical smell, and the static charge that accumulates on the screen, attracting dust. Offices start to sound different too, the clicking of keyboards, the hum of computers and monitors, the occasional beep of error messages or notification sounds. In schools, computer labs appear, rows of Apple IIs or Commodore 60s, students learning basic programming or playing educational games. The distinctive whir of disk drives and the glow of green or amber monitors become part of childhood for a new generation. They learn to type on real keyboards, to save their work to floppy disks that actually are floppy, the 5.25-inch kind that bend in your hand, before the rigid 3.5-inch disks that aren't really floppy at all despite the name. At home, families gather around computers. Games like King's Quest or Leisure Suit Larry load from multiple disk swaps. Insert disk 1, wait for it to load, swap to disk 2, wait again, swap back to disk 1. The process is slow, mechanical, but the result, interactive stories, colourful graphics, synthesized sounds, feels magical. The computer beeps and boops through its sound card, generating music that's recognisably musical but unmistakably electronic, limited by the technology but charming in its limitations. Through the night, bulletin board systems, BBSES, run on home computers, waiting for phone calls from modems. A single phone line means a single user at a time, so people check message boards and download files quickly, then disconnect to let others connect. SysOps, system operators, maintain these small digital communities, sometimes just a computer in a bedroom, sometimes elaborate setups with multiple phone lines, and huge, for the era, hard drives, storing files to share. Remember when computers filled rooms and required specialists to operate? Now they sit on desks, used by everyone from accountants to writers to children doing homework. The transition happens surprisingly fast. By the early 1990s, personal computers are becoming expected tools, not luxury items. Personal computer prices fall as manufacturing scales up and components commoditize. And something else is beginning to happen, quietly at first, but with revolutionary implications. Computers are starting to talk to each other. The internet age, connecting the world time, shifts again. You find yourself in a home office, mid-1990s. The computer, faster now, with a colour screen, perhaps running Windows 95, with its start button and taskbar, is connected to a small box that blinks with indicator lights. It's a modem, and you're about to witness something that will change everything. Connecting to the internet. The modem dials. You can hear it, the clicking of the relay as it picks up the phone line, the dial tone, the touch tone beeps as it dials the number, then the distinctive sound that becomes iconic, the screeching, warbling negotiation as the modems on each end establish a connection. It sounds like digital chaos, but it's actually two machines introducing themselves, agreeing on protocols, synchronizing their communication. It takes perhaps 30 seconds, then silence, or rather the soft hiss of the connection, data flowing as audio tones too rapid to hear as individual sounds. The screen shows a login prompt for an internet service provider. Type the username and password, press enter, wait. Text scrolls by, connecting, authenticating, welcome. You're online. The computer is now connected to other computers, part of a global network that's been growing quietly for decades, but is just now becoming accessible to ordinary people. The web browser loads, probably Netscape Navigator, with its distinctive throbbing N icon, or maybe Internet Explorer, coming free with Windows and slowly winning the browser wars. Web pages load slowly, painfully slowly by later standards, appearing line by line. Text first, then images filling in gradually from top to bottom. You can watch them load, see the scan lines appearing, wait patiently for a simple page to complete. The early web is text-heavy. Images are small and compressed. Videos are essentially impossible. Websites have guest books where visitors sign their names, hit counters showing how many people have visited, animated GIFs that sparkle or rotate. The design is often amateur, but it doesn't matter. What matters is that information that would have required a trip to a library is now accessible from home, that you can read news from around the world, that people are publishing pages about their interests and hobbies and research. Email becomes universal, not just within companies, but between them, across the world. Near instant communication that's faster than postal mail, more convenient than phone calls, leaving a written record. The morning routine changes again. Arrive at work, check email, respond to messages, send files as attachments, documents, spreadsheets, eventually photos and other media. Online shopping appears. Amazon starts selling books, then expands. eBay connects buyers and sellers in a vast digital marketplace. The idea of buying things without visiting a physical store seems strange at first. Trusting credit card numbers to the internet seems risky, but it works, and convenience overcomes caution. Payment happens through forms. Fill in the shipping address, the credit card number, click submit, wait for confirmation. Days later, a package arrives in physical mail, bridging digital and physical worlds. People track orders obsessively, checking status pages that update infrequently, learning patience in an era that's supposed to be instant. The language of the internet develops. URLs and hyperlinks, spam and cookies, bandwidth and latency. People learn new skills: how to search effectively, how to evaluate source credibility, how to recognize scams and hoaxes that spread through email forwards and chain messages. Don't believe everything you read online becomes parental advice, even as online sources grow more authoritative. Chat rooms form communities, people with shared interests gathering in virtual spaces, conversations scrolling by in real time, usernames becoming identities. Some rooms are busy around the clock, populated by users from different time zones, creating spaces that never sleep. Others are quiet most of the time, coming alive at specific hours, becoming digital third places where regulars gather. Forums organise discussions into threads. Someone posts a question or comment, others reply, conversations branch and deepen. The format encourages thoughtful responses. You have time to compose your thoughts, edit before posting, include links and quotes. Internet culture develops its own norms. Netiquette guides behaviour. FAQs answer common questions. Moderators maintain order in larger communities. Search engines organise the web's growing chaos. Early ones like AltaVista and Yahoo try to catalogue everything, but Google, arriving late, does it better with superior algorithms. Just Google it becomes a phrase replacing look it up in the encyclopedia. The world's information is becoming searchable, findable, accessible. The sounds of the internet era are distinctive. The modem handshake, the "you've got mail" announcement, the various beeps and chimes of instant messaging programs, the click of the mouse as you navigate between pages. The smell is unchanged from earlier computers, warm electronics, plastic, the slight ozone from monitors. But the experience is transformed. Late at night, the screen glowing in the dark, people explore this new digital space. They read forums and join discussions, make friends with people they'll never meet in person, discover communities built around shared interests. The internet is social before social media exists. Though bulletin boards and Usenet groups and IRC chat rooms aren't called social media yet. Teenagers talk to friends through AOL Instant Messenger or ICQ, away messages becoming tiny broadcasts of mood and status. The sounds are distinctive. The door creak when someone signs on, the oh when messages arrive, the varied notification sounds people customize to recognize who's messaging them without looking at the screen. Download culture emerges, sharing music through Napster, software through file-sharing networks, learning to navigate copyright questions and bandwidth limitations. A single song takes minutes to download on dial-up, hours for albums, overnight for software. People start downloads before bed, check progress in the morning, learning patience while simultaneously feeling the thrilling impatience of having access to nearly everything. The dot-com boom and bust happen. Massive investments in internet companies, stock prices soaring, then crashing when business models prove unsustainable. But the infrastructure remains: fibre optic cables crossing oceans, server farms in data centres, protocols and standards that will outlive individual companies. The internet survives its first boom-bust cycle, emerging more robust, more integrated into daily life. Through the late 1990s and early 2000s, the internet transitions from novelty to necessity. Businesses must have websites, Email becomes expected. Broadband arrives, cable modems and DSL replacing dial-up. Connections that are always on, no more modem handshakes. Faster speeds that make images and eventually video practical. The constant hiss of the dial-up modem is replaced by silence. The connection is just there, invisible, constant. The world is networking. Not just computers in offices, but computers in homes, all connecting to servers in data centers, creating a global mesh of communication and information and commerce. The foundation laid decades earlier, binary logic, transistors, integrated circuits, microprocessors, personal computers, has led here to a world where being offline is the exception, where information flows freely, where the boundaries between physical and digital spaces begin to blur. Remember those room-sized vacuum tube computers? Remember the transistors that replaced them? Remember the integrated circuits that packed thousands of transistors onto single chips? Remember the microprocessors that put entire computers onto chips? Remember the personal computers that brought computing to desks and homes? All of it led here to computers that are windows to a global network, tools for accessing humanity's collective knowledge and creativity. The circuits never rest, electrons flowing endlessly through silicon pathways, routing packets of data around the world at the speed of light, computing invisibly through the night. Somewhere a server is processing a request, responding in milliseconds, handling thousands of requests simultaneously, part of the vast infrastructure that makes the internet possible. But the story continues. Modern processors contain billions of transistors. Graphics cards have thousands of tiny processing cores, and these powerful machines are being turned to a new purpose, not just calculating and displaying and networking, but learning, recognizing patterns, generating text and images and sounds, approaching something that might be called intelligence. That story will have to wait for part 3. But rest now, knowing that the journey from mechanical gears to the networked world has been extraordinary, each generation building on the last, simple principles, creating endless complexity, patient engineering, accumulating into revolution. The machines compute on, tireless through the night, while the world sleeps. You now stand in modern times, though now is a moving target in the story of computing. It's the 2000s, then the 2000s, and the pace of change hasn't slowed. If anything, it's accelerated. The chips being manufactured today would seem like science fiction to the engineers who built those first transistors at Bell Labs. Imagine you're standing in a modern semiconductor fabrication facility. Though standing isn't quite right, because you're wearing a full cleanroom suit again, more advanced than the ones from the 1960s, in a facility that makes those early clean rooms look almost casual. The air filtration is extraordinary. Particles larger than 0.1 micrometers are removed. The yellow lighting is still there, still protecting photosensitive materials, but the processes happening here are working at scales that approach the atomic. Modern processors, billions of transistors in your pocket. The wafers are enormous now, 12 inches in diameter, some facilities working with even larger sizes. And on each wafer, hundreds of chips are being fabricated simultaneously, each chip containing not thousands of transistors, not millions, but billions. A modern smartphone processor might have 15 billion transistors. A high-end desktop CPU might have 30 billion or more. The numbers become almost meaningless. How do you visualize a billion of anything? Try this. If each transistor were a person, a single modern processor would contain more transistors than there are people on Earth, twice over. all of them switching on and off billions of times per second, all of them working together in carefully orchestrated patterns, all of them etched onto a piece of silicon smaller than a postage stamp. The manufacturing process has become almost incomprehensibly precise. The smallest features on these chips, the transistor gates, the metal traces connecting them, are measured in nanometers. 5 nanometers, 3 nanometers, sizes so small that quantum effects start to matter, that atoms can be counted. Extreme ultraviolet lithography uses light with wavelengths so short they're absorbed by air, requiring the entire process to happen in vacuum chambers. The photomasks are engineering marvels in themselves, defect-free patterns at near atomic scales. You watch through a window as robotic systems handle the wafers, moving them between process stations with sub-millimeter precision. Humans rarely enter the most critical areas. The risk of contamination is too high. Instead, engineers monitor from control rooms, watching parameters on screens, adjusting recipes for the hundreds of process steps each wafer requires. The room hums with the sound of machinery, vacuum pumps, cooling systems maintaining precise temperatures. The chips coming out of these facilities are extraordinary. They don't just contain billions of transistors, they contain multiple different types of processors working together. A modern smartphone chip might have several CPU cores for general computing, a GPU with hundreds or thousands of smaller cores for graphics and parallel processing, specialized neural processing units for machine learning tasks, image signal processors for the camera, secure enclaves for encryption, radio processors for cellular and Wi-Fi connections, all on a single piece of silicon, all working together seamlessly. Each section of the chip has its own purpose, optimized for specific tasks. The CPU cores are designed for serial computation, executing instructions one after another at incredible speeds, handling the operating system and applications, and all the unpredictable tasks a computer must perform. The GPU cores are simpler but numerous, designed for parallel work, processing thousands of pixels or vertices simultaneously, making real-time 3D graphics possible. The neural processing units contain specialized circuits for matrix multiplication and other operations common in machine learning, performing those operations orders of magnitude more efficiently than general-purpose cores could. The integration is seamless from a user's perspective, but internally it's a marvel of coordination. Different parts of the chip communicate through interconnects measured in bytes per second by the billions, sharing data at rates that would have required dedicated high-speed networks in earlier eras. Power management circuits constantly monitor what each section is doing, providing power only where needed, shutting down or slowing sections that aren't in use, balancing performance against battery life, against heat generation in real-time decisions made millions of times per second. The CPU cores themselves are marvels of design. They're not just executing instructions one at a time anymore. They're running multiple instructions simultaneously through pipelining and superscalar execution, predicting which way program branches will go and speculatively executing those paths, reordering instructions to avoid waiting for slow memory accesses, splitting single instructions into micro-operations that can be parallelized. A modern processor might have a dozen or more instructions in various stages of execution simultaneously, hiding the latency of each individual operation through sheer complexity. Cache memory has become crucial. Small, fast memory built directly into the processor, storing copies of frequently accessed data so the CPU doesn't have to wait for main memory. Modern processors have multiple levels of cache. L1 cache measured in kilobytes but accessible in just a few clock cycles. L2 cache measured in megabytes and slightly slower, L3 cache measured in tens of megabytes shared between cores. The memory hierarchy is carefully designed to give the illusion of infinite speed and infinite capacity, when in reality it's a delicate balance of trade-offs. Touch a modern smartphone. It's warm, but barely. The processors inside are more powerful than supercomputers from decades past, yet they run cool enough to hold against your face, efficient enough to last all day on a battery smaller than a deck of cards. The screen responds instantly to your touch, running 60 or even 120 frames per second, smooth and fluid. Behind that smoothness are billions of calculations, detecting your touch, determining what should happen, updating the display, all in milliseconds so short you never notice the computation. The sound of modern computers is mostly silence. No clicking relays, no whirring fans in most mobile devices, just the occasional haptic buzz of feedback. Even desktop computers run quietly compared to their ancestors, with carefully designed cooling systems and power management that slows processors when full speed isn't needed. But for the most demanding tasks, gaming, video editing, scientific computing, and especially artificial intelligence, more power is needed. Graphics cards, originally designed to render 3D graphics for games, have evolved into massively parallel computing devices, each containing thousands of small processing cores running simultaneously. A high-end GPU might have 10,000 cores, each one simpler than a CPU core, but collectively capable of performing trillions of operations per second. These GPUs find new purposes beyond graphics. Their parallel architecture makes them ideal for certain types of calculations: simulations, cryptography, password cracking, and most importantly, training artificial intelligence systems. In data centers around the world, racks of GPUs hum away, consuming kilowatts of power, generating heat that must be removed by elaborate cooling systems, all to teach machines to recognize patterns, to understand language, to generate images and text and sound. How machines learn, the mathematics of intelligence time shifts slightly. You find yourself contemplating something that would have seemed like pure science fiction to those engineers working with vacuum tubes. Machines that learn, that improve through experience, that perform tasks without being explicitly programmed for every situation. Tasks with artificial intelligence isn't new. Researchers have been pursuing it since the earliest days of computing. But what's changed is scale. Enough computing power, enough data, and algorithms that actually work when given sufficient resources. The foundation is something called a neural network, loosely inspired by how brains work, though the similarity is more metaphorical than literal. Imagine a simple neural network, layers of simulated neurons, each one a mathematical function that takes inputs and produces an output. The first layer receives data, maybe pixels from an image. Each neuron looks at its inputs, multiplies them by weights, adds them together, applies a non-linear function, and passes the result forward. The second layer does the same with the outputs from the first layer, and so on through multiple layers until the final layer produces an answer. This image contains a cat, or this image contains a dog. Initially the weights are random, and the network's answers are nonsense. But then you show it thousands, millions of examples, images labelled with what they contain. For each example you calculate how wrong the network's answer was, then adjust the weights slightly to make it more correct. This process, called backpropagation, works backwards through the layers, tweaking weights throughout the network. Do this millions of times with millions of examples, and gradually, mysteriously, the network learns to recognize patterns. the mystery is real. Even the researchers who design these systems can't fully explain why they work as well as they do, or exactly what patterns the networks have learned to recognize. The weights, billions of them in large networks, encode knowledge in a way that's opaque to human inspection. We can observe the inputs and outputs, measure the accuracy, but the internal representations remain largely inscrutable. Modern artificial intelligence systems are vast. GPT-3, a language model that can generate surprisingly human-like text, has 175 billion parameters, weights that had to be tuned through training. The training process took months, running on thousands of GPUs simultaneously, consuming electricity measured in megawatt hours, costing millions of dollars. The result is a system that seems to understand language, that can answer questions, write essays, translate between languages, even generate computer code. Imagine you're in a data center where such a model is being trained. The room is loud with cooling fans, warm despite the air conditioning, filled with racks of servers, each containing multiple GPUs. Indicator lights blink in patterns that mean something to the monitoring systems, but appear random to you. Cables connect everything: power, networking, cooling lines. The infrastructure supporting this computation is industrial in scale. Walk between the racks, and you feel the heat radiating from the servers despite the aggressive cooling. The air smells of electronics and the particular odour of high-performance computing equipment running at full capacity. The noise is constant: the whoosh of cooling fans, the hum of power supplies, the occasional click of a hard drive, or the beep of a status indicator. The floor is raised, allowing cooling air to flow up through perforated tiles, creating a gentle breeze around your ankles. The operations center for the data center is quieter, climate-controlled, dominated by screens showing status dashboards. Temperatures, power consumption, network traffic, compute utilization, all visualized in real-time graphs and statistics. Alerts scroll by when thresholds are exceeded, a server running hot, a network link saturated, a job taking longer than expected. Most are handled automatically by management software. Only the unusual cases require human intervention. Outside the building, power infrastructure supports the computation. Transformers stepping down voltage from the grid, backup generators ready to activate during outages, battery systems to bridge the transition, switchgear to route power where needed. The electrical consumption is measured in megawatts, comparable to a small town, all transformed into computation and ultimately into heat that must be expelled through cooling towers or radiators, making the data center a perpetual transformer of electricity into information. The training process is iterative. Feed text through the network, calculate how well it predicted the next word, adjust the weights, repeat. Billions of times, with billions of examples, the weights gradually shift toward configurations that make better predictions. Progress is measured in loss curves, graphs showing how wrong the network is over time, hopefully decreasing, approaching, but never quite reaching perfection. What emerges from this process is remarkable. The trained model can complete sentences naturally, answer questions about topics it's never been explicitly taught, generate coherent arguments, even show something that looks like reasoning. It's not consciousness. Researchers are careful to emphasize this, but it's also more than simple pattern matching. Exactly what it is remains philosophically puzzling. These systems find applications everywhere. Voice assistants that understand spoken commands, using neural networks to convert sound to text and to understand meaning. Image recognition systems that can diagnose medical conditions from X-rays, sometimes more accurately than human doctors. recommendation systems that suggest what to watch or read or buy, learning from millions of users' behaviour. Language translation that's finally good enough to be genuinely useful, bridging languages in real time. Self-driving cars use multiple neural networks simultaneously, some analysing camera images to identify other vehicles, pedestrians, lane markings, others processing LiDAR data to build 3D models of the environment, others planning routes and controlling acceleration and steering. All of this happens in real time, multiple times per second, running on specialised hardware in the vehicle, making decisions that must be both accurate and fast. The training data for these systems is enormous. Self-driving cars are trained on millions of miles of driving data. Image recognition systems learn from billions of labelled images. Language models consume most of the text available on the internet. The scale is staggering, and it raises questions about privacy, about bias in the training data, about the environmental cost of all this computation, about what happens when systems trained on human-generated data start to influence the new data humans generate. But the capabilities keep expanding. Systems that generate realistic images from text descriptions, creating artwork that's sometimes indistinguishable from human-created art. Systems that predict protein folding, solving problems in biology that had stumped researchers for decades. Systems that play games, chess, Go, StarCraft, at superhuman levels, discovering strategies that surprise even expert players. The irony is that these intelligent systems are built from the same basic components as the simplest circuits. Transistors switching on and off, binary logic, patterns of ones and zeros. Intelligence, or something that looks like intelligence, emerges from quantity and organisation, from billions of simple operations performed in carefully designed patterns, from learning algorithms that gradually tune billions of parameters toward useful configurations, from transistors to thoughts. The philosophical wonder reflect now on the journey you've taken through this long night. You started with mechanical calculators, brass gears and levers, clicking methodically through arithmetic. You watched vacuum tubes glow orange in room-sized computers, switches controlled by electricity instead of by hand. You saw transistors shrink those computers, then saw integrated circuits shrink them further, packing thousands, then millions, then billions of transistors onto single chips. You witnessed the birth of the microprocessor, entire computers on chips smaller than postage stamps. You watched personal computers spread from hobbyist basements to every desk and home. You experienced the internet connecting those computers into a global network, information flowing at light speed between machines across the world. And you've arrived at artificial intelligence, systems that learn from experience, that recognize patterns in data, that generate text and images and predictions, built from nothing but mathematics and silicon, electricity flowing through circuits at speeds and scales that would astound those early engineers. The progression is remarkable. Binary switching, on or off, 1 or 0, voltage present or voltage absent, is the simplest possible computation. Yet build enough layers of it, organize it correctly, give it sufficient scale, and complexity emerges. Logic gates combine into arithmetic units. Arithmetic units combine into processors. Processors execute instructions. Instructions combine into programs. Programs combine into operating systems and applications. Applications process data in ways that start to look intelligent. At each level of abstraction, new properties emerge that weren't obvious from the level below. A single transistor just switches. A logic gate performs a simple operation. but combine billions of logic gates in the right configuration, run them billions of times per second, and you get computers that can simulate weather patterns, render photorealistic graphics, understand speech, compose music, play chess, drive cars. The philosophical questions are genuine. Is there a fundamental difference between human intelligence and machine intelligence, or is it just a matter of scale and organization? Do these neural networks actually understand, or are they just sophisticated pattern matchers? Where is the boundary between programmed behavior and genuine learning, between following rules and having insight? These questions don't have clear answers, and perhaps that's appropriate. The line between mechanism and mind has always been blurry. Babbage imagined mechanical intelligence. Turing asked if machines could think. And now we have systems that pass many tests of intelligence while still clearly being machines, silicon and software, deterministic at the lowest level, yet seemingly creative and flexible at higher levels. What's certain is that computing has become woven into the fabric of modern life in ways that are both obvious and invisible. The quiet revolution. Computers everywhere. It's late now. You stand in a world transformed, though the transformation happened so gradually that it's easy to miss. Look around. Computers are everywhere, in forms that might not even be recognized as computers. Your phone is a computer more powerful than the room-sized machines from the vacuum tube era, running an operating system more sophisticated than what desktop computers had just decades ago. It contains multiple processors, gigabytes of memory, wireless radios connecting to cellular networks, and satellites and local devices. It tracks your location, monitors your health through sensors, captures photos and videos, plays music and movies, provides access to essentially all human knowledge through the internet. And it fits in your pocket, runs all day on a small battery, costs a fraction of what those early computers did. Your car contains dozens of computers, one managing the engine, another controlling the transmission, others handling braking and steering assistance and climate control and the entertainment system. They communicate over internal networks, sharing data about speed and acceleration and driver inputs, coordinating their actions to make the car safer and more efficient than purely mechanical vehicles. Your home has computers embedded in appliances, the thermostat learning your preferences and adjusting temperatures automatically, the TV streaming content from internet servers, the doorbell containing a camera and network connection, the refrigerator potentially connected to the internet, though whether that's useful remains debatable. Even simple devices contain microcontrollers, the coffee maker, the microwave, the washing machine, each with a small processor running embedded software. The infrastructure supporting modern life runs on computers. The electrical grid balances supply and demand through networked control systems, routing power efficiently, detecting and isolating failures. The banking system processes billions of transactions through computers, money existing primarily as numbers in databases, transferred electronically rather than physically. Air traffic control tracks thousands of flights simultaneously, coordinating takeoffs and landings, ensuring safety through real-time data processing. The internet itself is a massive distributed computer system, millions of servers in thousands of data centers connected by fiber optic cables crossing oceans and continents, routers directing packets of data along optimal paths, all working together to create the illusion of instant access to information regardless of where it physically resides. Behind every web search, every social media post, every video stream are computers processing requests, databases storing data, algorithms deciding what to show you, databases The morning routine has changed completely from the pre-computer era. Wake up to an alarm on your phone, check messages and news while still in bed. The coffee maker you programmed the night before has already brewed coffee. Your car's navigation system plans the route to work, avoiding traffic it learned about from other cars reporting their speeds. At work, you sit at a computer all day, communicating through email and chat, working in documents and spreadsheets that exist only as data, attending meetings through video calls with colleagues on other continents. The rhythm of modern life is mediated by notifications, messages arriving, emails requiring responses, calendar reminders, social media updates, news alerts. Each one generated by software running on servers, transmitted through networks, delivered to your device with sounds or vibrations designed to capture attention. The constant connectivity changes how work happens, how relationships are maintained, how time is structured. Shopping happens through computers, searching for products, comparing prices, reading reviews written by other users and ranked by algorithms, adding items to virtual carts, checking out with payment information stored in encrypted databases. The physical delivery follows days later, but the decision and transaction happen in seconds, mediated entirely by software and networks and databases tracking inventory and managing logistics. Entertainment flows through computers, billions of songs available instantly through streaming services, more movies and shows than you could watch in multiple lifetimes, games ranging from simple puzzles to complex virtual worlds with thousands of simultaneous players. The recommendation algorithms suggest what to consume next, learning from your choices, shaping your experience through invisible curation. Social connection moves through computers, messages replacing phone calls, photos shared instantly with friends across the world, video calls making distance irrelevant, social networks maintaining loose connections with hundreds of acquaintances. The nature of friendship changes when maintenance is easier but also more superficial, when presence is simulated through text and images and video rather than physical proximity. Even entertainment is mediated by computers, streaming services that suggest what to watch based on viewing history, video games with photorealistic graphics and online multiplayer, music customized to your taste by algorithms, books read on electronic screens or listened to through synthetic voices that sound increasingly natural. And it's all built on the same foundation you've explored tonight. Transistors switching on and off, binary logic, circuits executing instructions, layers of abstraction from hardware to software to applications. The same principles that made ENIAC work make your phone work, just scaled up by factors of billions, miniaturized beyond what those early engineers could have imagined possible. The revolution is quiet because it's complete. Computing isn't a special activity anymore, it's woven into everything. Being offline is the exception. Carrying a computer is expected. Having constant access to information is assumed. The digital and physical worlds have merged to the point where distinguishing between them becomes difficult. Remember those Harvard computers, mostly women, calculating stellar positions by hand? Remember the operators rewiring ENIAC for each calculation? Remember the excitement of early PC owners loading programs from cassette tapes? Each era felt modern to those living through it, yet from the distance of time we can see the progression, the acceleration, the compound improvements building on each other. The future arrives gradually. What comes next? What comes next remains uncertain, though some directions are emerging. Quantum computing, working not with bits that are 0 or 1, but with qubits that can be both simultaneously, leveraging quantum superposition and entanglement to solve specific problems exponentially faster than classical computers. The machines are temperamental, requiring cooling to near absolute zero, isolated from environmental noise, but for certain problems. Cryptography, drug discovery, optimization, they show promise. Neuromorphic chips, designed to work more like biological brains with neurons and synapses, potentially more efficient than traditional processors for AI tasks. Biological computing using DNA or proteins as computational substrates. These are research directions, not products, but they suggest that silicon transistors might not be the final answer, that the progression from vacuum tubes to transistors to integrated circuits to microprocessors might continue into fundamentally different computing substrates. Moore's law that transistor counts double every couple years has slowed. The physics of making smaller transistors becomes harder as features approach atomic scales. But computing progress doesn't require Moore's law to continue. There's specialization with chips designed for specific tasks like neural network processing or graphics or signal processing, each optimized for its purpose. There's better software, algorithms that accomplish more with the same hardware. There's parallelism, thousands of processors working together on shared problems. The integration continues, sensors everywhere measuring everything, networks connecting it all, machine learning systems finding patterns in the data, automation handling routine tasks. Augmented reality overlaying digital information on physical space. Virtual assistants becoming more capable, more natural. Robots entering more domains, from warehouses to homes to eventually perhaps everywhere humans don't want to or can't be. The ethical questions grow alongside the capabilities. Privacy in a world where computers track everything. Bias in systems trained on historical data that reflects historical inequities. The environmental cost of computation, data centers consuming significant percentages of electrical grids, rare earth metals required for electronics, the challenge of electronic waste, the displacement of human labor by automation, the risk of AI systems that are powerful but not aligned with human values. These are human questions, not technical ones, though they arise from technical capabilities. They require wisdom, not just engineering, and they're questions without final answers, requiring continuous thought and adjustment as capabilities continue to evolve. But perhaps on this night journey through computing history, the appropriate note to end on isn't uncertainty about the future, but wonder at what's already been accomplished. From mechanical gears to quantum bits, from human computers to artificial intelligence, from calculation as tedious labour to computation as ubiquitous infrastructure. Each generation built on the last, solving problems and creating new possibilities, simple principles accumulating into astonishing complexity. The circuits that never rest. The circuits rest now, or rather they never rest. Somewhere a processor is executing instructions, billions of operations, completing in the time it takes you to breathe once. Somewhere data is flowing through fibre optic cables at light speed, packets being routed across continents, information finding its destination through the global network. Somewhere an AI system is training, weights being adjusted infinitesimally, learning from another batch of examples, gradually improving at its task. In data centers, servers hum through the night, cooling fans running constantly, processing requests from users in different time zones, streaming videos, running database queries, hosting websites, training machine learning models. The indicator lights blink in patterns, green for activity, amber for warnings, red for errors that need attention. Technicians monitor dashboards, responding to alerts, replacing failed components, keeping the infrastructure running. In homes around the world, phones charge on bedside tables, maintaining connections to cellular towers, syncing data in the background, ready to wake their owners with alarms calculated to optimize sleep cycles. Laptops sleep, but not deeply, maintaining memory state, ready to wake instantly when opened. The internet never sleeps, always available, always processing, a global nervous system for civilization. The computational substrate that supports modern life runs continuously, mostly invisibly, rarely thought about until it stops working. It's become infrastructure like electricity or water, expected to be available, noticed only in absence. But unlike those earlier utilities, computing continues to evolve rapidly, new capabilities emerging yearly, pushing into new domains, solving new problems, raising new questions. And all of it, every search, every message, every streamed video, every AI-generated image, every self-driving car decision, all of it happens through the coordinated switching of transistors, billions of tiny electronic switches turning on and off, implementing binary logic, executing instructions, storing and retrieving data. Patterns of ones and zeros transforming inputs to outputs according to rules encoded in silicon and software. From Babbage's brass gears that never quite worked, through glowing vacuum tubes filling rooms with heat, through revolutionary transistors smaller than peas, through integrated circuits packing thousands, then millions, then billions of transistors onto fingernail-sized chips, through microprocessors putting entire computers on single chips, through personal computers bringing computing to homes, through networks connecting those computers globally, through machine learning systems that approach something resembling thought. The journey has been extraordinary. Each step built on previous steps. Each generation of engineers solved their era's problems and handed new possibilities to the next generation. Each level of abstraction hid complexity while enabling new complexity to be built above it. Simple became complex, became simple again at higher levels, layers accumulating until switches became circuits, became processors, became computers, became networks, became intelligence, or something close enough to intelligence that the distinction blurs. Rest now, as the machines calculate on, tireless through the night. The electrons flow through silicon pathways, fast as lightning but patient as geology, one operation after another, billions per second, accumulated into tasks and programs and applications and services that shape the modern world. The computation continues, invisible and essential, the digital foundation beneath everything else, built from nothing but sand and metal and mathematics and human ingenuity. Sleep now. The circuits will still be running when you wake. They'll be running while you sleep, processing and calculating and learning the quiet revolution that transformed everything, one transistor at a time.